The Grandfather Paradox, a complete examination. Introduction. The Grandfather Paradox stands as one of the most intriguing thought experiments concerning time travel. First formulated by science fiction writer René Barjavel in 1943, this paradox exposes fundamental contradictions in our understanding of causality when considering backward time travel. At its core, it questions whether changing past events could create logical inconsistencies that unravel reality itself. Understanding the paradox. The classic formulation presents this scenario. 1. A time traveler journeys to the past. 2. They encounter their paternal grandfather before he has children. 3. The traveler kills their grandfather. 4. This prevents the grandfather from fathering the traveler's parent. 5. Consequently, the time traveler would never be born. 6. But if they were never born, they couldn't have traveled back to commit the act. This creates an unsolvable loop where the effect, killing grandfather, negates the cause, time traveler's existence. The paradox demonstrates that certain actions in the past could generate impossible contradictions in the timeline. Variations of the paradox. While the grandfather version is most famous, several equivalent paradoxes exist. The Hitler paradox, traveling back to kill Hitler before WW2. The self-prevention paradox, preventing your own birth. The information paradox, bringing future knowledge to the past that then prevents that knowledge's creation. Each variation follows the same fundamental structure where a time traveler's actions in the past would prevent the circumstances that enabled their time travel. Scientific perspectives. Physicists have approached the paradox through multiple theoretical frameworks. 1. General relativity. Einstein's equations allow for closed time-like curves, CCCs, potential pathways for time travel. However, most solutions require exotic matter with negative energy, infinite-length rotating cylinders, wormholes with specific properties. These remain theoretical with no experimental evidence. 2. Quantum mechanics. Some interpretations suggest quantum effects might resolve the paradox. The self-consistent Novikov principle asserts only consistent timelines can exist. Quantum superposition could allow both outcomes simultaneously. 3. Many worlds interpretation. This quantum theory proposes that all possible outcomes occur, just in separate universes. Applied to time travel, killing your grandfather would create a new timeline branch. Your original timeline remains unaffected. You wouldn't vanish, but the new universe would have no version of you. Philosophical implications. The paradox raises profound questions about 1. Causality. Challenges the fundamental principle that causes must precede effects. If time travel allows effects to influence causes, our understanding of causality breaks down. 2. Free will. If you cannot change past events without creating paradoxes, does free will truly exist? Or are all time travel events predetermined? 3. Identity and existence. Questions what constitutes personal identity if your existence can be retroactively erased. Proposed resolutions. Scientists and philosophers have proposed several solutions. 1. Self-consistency. Novikov principle. The universe automatically prevents paradoxes. Any attempt to create a contradiction would fail through unlikely coincidences preventing the act. Physical impossibilities arising at the crucial moment. The traveler being unable to complete the paradox causing action. 2. Multiple timelines, parallel universes. Each change creates an alternate timeline. Original history remains unchanged. New timeline branches with different events. Eliminates paradox by separating consequences. 3. Predestination. All time travel events were always part of history. Your actions in the past already happened. You were always part of the events you tried to change. Creates stable time loops instead of paradoxes. 4. Temporal protection, conjecture. Stephen Hawking proposed the universe prevents time travel through quantum mechanics preventing paradoxes, physical laws making time travel impossible, chronology protection at the Planck scale. 5. Immutable timeline. The past cannot be changed. Time travelers were always part of history. Any attempts to change events already happened. Creates a single, consistent timeline. Mathematical modeling. Recent work in theoretical physics has attempted to mathematically model paradoxes. 1. Deutsch's quantum time travel. Using quantum computing principles, shows information can be sent to the past without contradictions through quantum entanglement. 2. Post-selected time travel. Requires that only self-consistent outcomes are allowed, mathematically eliminating paradox possibilities. 3. Wormhole calculations. Certain wormhole solutions in general relativity appear to naturally prevent paradox formation through topological constraints. Cultural impact. The grandfather paradox has significantly influenced popular culture. 1. Literature. Featured in classic time travel stories like The Time Machine. Central to many science fiction novels exploring causality. 2. Film and television. Back to the Future trilogy explores paradox concepts. 12 Monkeys examines predestination aspects. Dark. Netflix builds entire narrative around paradoxes. 3. Video games. Chrono Trigger features paradox-based gameplay. Time Splitters series incorporates paradox elements. Braid uses time mechanics that create paradox-like situations. Current scientific consensus. While entertaining as a thought experiment, most physicists believe 1. Time travel to the past is likely impossible due to thermodynamic constraints, quantum mechanical prohibitions, lack of evidence for time travelers. 2. If possible, paradoxes would be prevented by physical laws we don't yet understand, universe-enforced consistency, multiple timeline branching. 3. The paradox primarily serves as a valuable conceptual tool, a test for physical theories, a boundary marker for possible physics, future research directions. Ongoing scientific work includes 1. Quantum gravity theories. Attempting to reconcile general relativity with quantum mechanics may provide answers about time travel possibilities. 2. Closed time-like curve research. Examining whether CTC could exist without creating paradoxes. 3. Quantum information experiments. Testing how information behaves in scenarios mimicking time travel situations. The grandfather paradox remains one of the most compelling thought experiments in physics and philosophy. While we currently lack definitive answers, examining the paradox has advanced our understanding of causality, pushed the boundaries of theoretical physics, inspired countless creative works, forced us to confront fundamental questions about reality. Whether time travel to the past becomes possible or remains fiction, the grandfather paradox will continue to challenge our conceptions of time, existence, and the fundamental nature of the universe. The bootstrap paradox, ontological paradox, a time travel conundrum. The bootstrap paradox, also known as the ontological paradox, is one of the most fascinating and mind-bending concepts in theoretical physics and philosophy, particularly in discussions about time travel. Unlike paradoxes that create contradictions, like the grandfather paradox, the bootstrap paradox creates a strange loop of existence where an object, piece of information, or event exists without any discernible origin. It's as if the item or information bootstraps itself into existence, hence the name. How the bootstrap paradox works. Imagine a time traveler goes back in time and gives Beethoven a copy of his complete symphonies. Beethoven then publishes these works as his own. The question then arises, who actually composed Beethoven's symphonies? They weren't created by Beethoven in this scenario, but they also weren't created by the time traveler who merely transported them. The music exists in a loop with no true point of origin. This is the essence of the bootstrap paradox: information or objects that exist without ever having been created. The term comes from the phrase pulling yourself up by your bootstraps, an impossible task that metaphorically represents this paradox's impossible origin. Types of bootstrap paradoxes. 1. Information paradox. A piece of information is sent back in time, and that information continues to be passed along until it reaches the original time traveler, who then sends it back. For example, a man receives a secret code from his future self that saves his life. Later, he travels back in time to give that same code to his past self. The code's origin cannot be traced. It simply exists in a loop. Object paradox. A physical object is sent back in time, creating an infinite loop of existence. The most famous example might be the uncreated artifact, like a time traveler who finds a mysterious pocket watch in an antique shop, then later travels back in time and leaves that same watch in the same shop, where his younger self will eventually find it. 3. Event paradox. An event causes itself through time travel. For example, a time traveler attempts to prevent a fire, but instead causes the very fire they were trying to prevent. The fire has no original cause outside of the time loop. Famous examples in fiction. Many science fiction stories have explored the bootstrap paradox. In The Time Traveler's 1964, a man gets a book containing the theory of time travel from a future version of himself. He later publishes the book, which eventually makes its way back to his past self. The television series Dark, 2017-2020, uses the bootstrap paradox extensively, particularly with a time travel book that seems to have no author. In Somewhere in Time, 1980, a man receives a pocket watch from an old woman, then later travels back in time and gives that same watch to her when she was young. The movie Predestination, 2014, features one of the most complex bootstrap paradoxes involving identity and parenting. Philosophical implications. The bootstrap paradox raises profound questions about 1. Causality. Our normal understanding of cause and effect breaks down when effects can precede their causes or when causes seem to disappear altogether. 2. Ontology, the nature of being. How can something exist without ever having been created? This challenges fundamental notions about existence and creation. 3. Free will. If events are predestined in these loops, do individuals truly have free will, or are they just playing out predetermined role? 4. Identity. In extreme cases, like in predestination, the paradox can challenge our very notions of personal identity and individuality. Physics. Perspectives. From a physics standpoint, the bootstrap paradox relates to 1. Closed time-like curves, CCCs, solutions in general relativity that theoretically allow for time travel to the past. The bootstrap paradox shows what might happen if these CCCs were possible. 2. The Novikov self-consistency principle. Russian physicist Igor Novikov proposed that any actions taken by a time traveler were already part of history, meaning paradoxes couldn't occur. The bootstrap paradox fits this principle since it's consistent, just, originless. 3. Quantum mechanics. Some interpretations suggest that quantum particles could experience similar paradoxes existing in states without clear causal origins. Potential resolutions. Physicists and philosophers have proposed several ways to resolve or interpret the bootstrap paradox. 1. The self-consistent universe. The universe simply doesn't allow contradictions, so bootstrap loops are permitted as long as they're consistent. The paradox isn't really a problem, but just a strange feature of time travel. 2. Multiple timelines. In some interpretations, time travel creates alternate timelines, so the original version of information or objects exists in a different, now inaccessible timeline. 3. Quantum origin. Some theories suggest that bootstrapped items might emerge from quantum fluctuations when the time loop is created. 4. Simulation theory. If we're in a simulation, bootstrap paradoxes could be programming glitches or intentional features. Why the paradox matters? The bootstrap paradox isn't just an entertaining thought experiment. It has real implications for how we understand. 1. The nature of time. It challenges our linear perception of time and suggests time might be more complex than we experience. 2. Information theory. What does it mean for information to be created if it can exist without an origin point? 3. Creativity and invention. If information can be bootstrapped, it raises questions about the nature of human creativity and originality. 4. The origins of the universe. Some have drawn parallels between the bootstrap paradox and cosmological questions about the origin of the universe itself. Could the universe have created itself in a similar bootstrap fashion? Personal identity paradoxes. In extreme versions, the bootstrap paradox can affect not just objects or information, but people themselves. The most dramatic example is a person who becomes their own ancestor through time travel loops, leading to questions about how much of their DNA comes from where? Who were their original parents? Are they truly the same person at different points in the loop? These scenarios push our concepts of identity to their breaking points. Temporal mechanics and the bootstrap. The paradox also relates to theories about how time might work. 1. The block universe theory. If all time exists simultaneously, bootstrap loops are just features of this eternal structure. 2. Time as a dimension. Just as we can move in circles through space, bootstrap paradoxes suggest we might move in circles through time. 3. Conservation of information. Physics suggests information can't be created or destroyed. Bootstrap paradoxes might be one way this plays out in time travel scenarios. Conclusion. The bootstrap paradox remains one of the most intriguing thought experiments about time travel. Unlike paradoxes that create contradictions, it presents us with consistent but originless existence, a concept that challenges our deepest notions about reality, creation, and causality. Whether as a plot device in fiction or a serious consideration in theoretical physics, the bootstrap paradox shows that time travel, if possible, would lead to situations far stranger than we might imagine. It serves as a reminder that our everyday experience of linear time and clear causation might be just one part of a much more complex temporal reality. As we continue to explore the nature of time through physics and philosophy, the bootstrap paradox stands as both a warning about the strange consequences of time travel and an invitation to think more deeply about where things, and even we ourselves, truly come from. The Fermi paradox, the eerie silence of the universe. Introduction. The Fermi paradox is the apparent contradiction between the high probability of extraterrestrial civilizations existing in the universe and the complete lack of evidence for such civilization. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a 1950 lunchtime conversation, this paradox has puzzled scientists, philosophers, and the general public for decades. Given the vast number of stars in our galaxy, 400 billion, and the even more staggering number of galaxies in the observable universe, about 2 trillion, the statistical likelihood suggests we should have encountered alien life by now. Yet, we see no signs, hear no signals, and have found no evidence of other intelligent life forms. The Drake equation. To understand the Fermi paradox, we must first examine the Drake equation, formulated by astronomer Frank Drake in 1961. This probabilistic formula estimates the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. NJK, RAUI, Jo, FP, HIA, NESHO, FIO, FICO, FC, CORO, F. Where we? RIAI, average star formation rate, FP key traction of stars with planetary systems, net number of planets that could support life per star, LAF fraction of planets where life actually appears, 5D fraction of life-bearing planets where intelligence evolves, FCKA fraction of civilizations that develop detectable technology, L length of time such civilizations release detectable signals. Even with conservative estimates, the equation suggests there should be numerous civilizations in our galaxy alone. Yet we observe none. This is the heart of the paradox. Possible solutions to the paradox. Scientists have proposed numerous hypotheses to explain the Fermi paradox, which generally fall into two categories. Those suggesting intelligent life is rare or non-existent, and those suggesting it exists but we can't detect. Here are the most prominent explanations. Category 1. We're alone or life is extremely rare. 1. The rare Earth hypothesis. This suggests that while microbial life might be common, the conditions required for complex, intelligent life are extraordinarily rare. Factors like being in a galactic habitable zone, not too close to the center, having a Jupiter-like planet to deflect asteroids, plate tectonics for climate regulation, a large moon for tidal forces and axial stability, evolutionary bottlenecks that make intelligence unlikely. 2. The Great Filter. This proposes that there's some extremely difficult step in the evolution of life that prevents civilizations from reaching interstellar communication. This filter could be behind us, abiogenesis, emergence of complex cells. Ahead of us, perhaps all advanced civilizations destroy themselves. The frightening implication is that if the filter is ahead of us, humanity may face an existential catastrophe. 3. Intelligence is unlikely. Evolution doesn't aim for intelligence. It took 4 billion years on Earth. Maybe most life stays microbial or never develops technology. Category 2. Civilizations exist, but we don't see them. 4. The zoo hypothesis. Advanced civilizations know we're here, but choose not to contact us, perhaps to allow natural development, or as part of a galactic conservation policy. 5. The dark forest hypothesis. Inspired by Liu Cixin's sci-fi trilogy, this suggests civilizations hide, because broadcasting your location is dangerous, in a universe where other civilizations might be hostile. 6. Technological singularity. Advanced civilizations may have transitioned to post-biological forms, AI, uploaded consciousness, that we can't recognize or detect. 7. Brief window of detectability. Perhaps civilizations only broadcast detectable signals for a short period, a few hundred years, before switching to undetectable technology, making the chances of overlapping very small. 8. They're already here. UFO hypotheses. While lacking scientific evidence, some propose aliens are already observing Earth, but remain hidden. 9. Communication incompatibility. Alien communication methods might be so advanced or different that we can't recognize them as artificial. 10. Galactic colonization is impossible. The distances and energy requirements for interstellar travel might make galactic empires physically impossible, limiting civilizations to their home systems. Historical and philosophical context. The Fermi paradox isn't just a scientific question. It has deep philosophical implications. Copernican principle challenges the idea that we're not special. If we're alone, we are special. Anthropic principle. Maybe the universe is fine-tuned for life, but only barely. Existential risk highlights potential dangers to technological civilizations. Meaning of life. If we're alone, does that give humanity special responsibility? Recent developments. In recent years, several factors have intensified the Fermi paradox debate. 1. Exoplanet discoveries. The Kepler telescope revealed that planets are extremely common, with most stars having planets in habitable zones. This makes the absence of life even more puzzling. 2. SETI's continued null results. Decades of searching for radio signals have found nothing, despite increasing technological capabilities. 3. Astrobiology advances. Discoveries of extremophiles on Earth and potential biosignatures on Mars and Europa suggest life might arise easily, deepening the paradox. 4. The wow! The famous 1977 signal remains unexplained but never repeated, highlighting how rare even potential detections are. Statistical perspectives. From a purely statistical viewpoint, wazoo, there are more planets than grains of sand on all Earth's beaches. Even if only 0.1% of planets develop life, there should be millions of civilizations. Our galaxy is 13 billion years old, plenty of time for civilizations to arise and spread. Even at 1% the speed of light, the galaxy could be colonized in 10 million years. This makes the silence even more perplexing. Potential future resolutions. Several upcoming scientific developments might help address the paradox. 1. James Webb Space Telescope may detect biosignatures in exoplanet atmospheres, telling us if simple life is common. 2. Advanced SETI projects. New telescopes like the Square Kilometer Array could vastly improve our search capabilities. 3. Mars sample return. Finding fossil or extant life on Mars would support the idea that life arises easily. 4. Breakthrough starshot. Sending tiny probes to nearby stars could provide direct evidence of life in other systems. Cultural impact. The Fermi paradox has significantly influenced culture. Science fiction, works like Contact, 2001, A Space Odyssey, and Arrival explore themes from the paradox. Scientific funding motivates SETI and astrobiology research. Existential thought affects how we view humanity's place in the universe. Global risk studies influences concerns about nuclear war, AI, and other existential threats. Criticisms of the paradox. Some scientists argue the Fermi paradox isn't a true paradox because 1. Our sample size is small. We've only seriously searched for life for a few decades, a cosmic blink of an eye. 2. Detection biases. Our technology might be too primitive to detect alien civilizations. 3. Anthropomorphic assumptions. We assume aliens would think and behave like humans, which may be incorrect. 4. Timescale issues. Civilizations might rise and fall too quickly to overlap with ours. The Fermi paradox and humanity's future. The paradox forces us to confront several possibilities about our future. 1. If we're alone, we may be responsible for spreading life in the universe. 2. If the great filter is ahead of us, we need to identify and survive it. 3. If civilizations inevitably destroy themselves, we must learn to avoid this fate. 4. If advanced civilizations are hiding, we should consider why and what that implies. Conclusion. The Fermi paradox remains one of the most profound unanswered questions in science. As we continue to explore our solar system and develop more sophisticated search methods, we may someday find an answer, whether through detecting distant life, discovering alien artifacts, or confirming our solitary existence in the cosmos. Until then, the eerie silence of the universe serves as both a humbling reminder of our possible uniqueness and an urgent motivation to preserve and understand our own civilization. The paradox challenges our assumptions about life, intelligence, and technology, while highlighting how much we still have to learn about the universe and our place within it. The Barber paradox and Russell's paradox. Complete explanation. Introduction. The Barber paradox is a famous logical puzzle that reveals deep problems in how we define collections and categories. Created by mathematician Bertrand Russell in the early 1900s, This simple story about a village barber actually demonstrates a major flaw in early set theory that forced mathematicians to rebuild the foundations of their field. The basic paradox. Imagine a small town with these rules. There is one male barber in town. This barber shaves all men who don't shave themselves. He shaves only those men. Now consider, does the barber shave himself? If yes, then he shaves himself. But he only shaves men who don't shave themselves. So he cannot shave himself. If no, then he doesn't shave himself. But he shaves all men who don't shave themselves. So he must shave himself. This creates an unsolvable contradiction. The barber cannot consistently either shave or not shave himself. Russell's original version. The barber story is actually a simplified version of Russell's more technical paradox about sets. Consider the set of all sets that don't contain themselves. Does this set contain itself? If yes, then it should not contain itself, by definition. If no, then it should contain itself, because it doesn't. This showed that naive set theory, which allowed any defined collection to be a set, led to impossible contradictions. Why this matters. 1. Broke early set theory, showed existing rules led to paradoxes. 2. Forced new foundations, led to axiomatic set theory. 3. Revealed self-referenced dangers, showed circular definitions cause problems. 4. Influenced computer science, affected how we handle recursive logic. Mathematical solutions. 1. Axiomatic set theory, ZFC system. Adds careful rules about set creation. Prevents too big collections like set of all sets. Uses axiom of separation to control definitions. 2. Type theory, Russell's solution. Creates hierarchy of types. A set can't contain things at its own level. Blocks the self-reference that causes paradoxes. 3. Rejection approach. Some argue such definitions are meaningless. The barber and set of all sets are invalid concepts. They create nonsense questions with no answer. Related paradoxes. 1. The librarian paradox. A catalog lists all books that don't list themselves. Should the catalog include itself? 2. The rule-maker problem. A leader makes all rules not made by others. Who makes the rule about rule-making? 3. The Grelling-Nelson paradox. Some words describe themselves. Short is short. Others don't. Long isn't long. Does heterological, meaning doesn't describe itself, describe itself? Real-world applications. 1. Computer science. Helps prevent infinite loops in programming. Influence-type systems in languages like Haskell. Related to the halting problem in computation. 2. Law and governance. Shows problems with self-referential laws. Exposes issues in regulations that try to govern themselves. 3. Philosophy of language. Demonstrates limits of definitions. Shows not all grammatically correct statements make sense. Impact on mathematics. Russell's discovery. Forced mathematicians to rebuild set theory. Led to more rigorous formal systems. Inspired Gödel's work on incompleteness. Changed how we think about mathematical truth. Philosophical implications. 1. Nature of truth. Shows some statements can't be true or false. Reveals limits of formal systems. 2. Definition problem. Demonstrates dangers of circular definitions. Shows language can create false problems. 3. Knowledge limits. Proves some questions have no consistent answer. Reveals boundaries of what we can formally define. Cultural appearances. 1. In literature. Featured in Hofstadter's Gödel, Escher, Bach. Appears in many logic puzzle collections. 2. In popular culture. Referenced in TV shows about logic. Used in mystery stories with paradoxical elements. 3. In education. Common example in philosophy classes. Used to teach about logical fallacies. Modern perspectives. Today, the paradox helps us understand how to build consistent formal systems, the importance of preventing self-reference, the boundaries between meaningful and meaningless questions. Conclusion. The Barber paradox, while simple to state, revealed profound truths about mathematics, logic, and language. By exposing flaws in early set theory, it forced mathematicians to develop more rigorous systems. Its lessons continue to influence computer science, philosophy, and our understanding of formal systems. Ultimately, it teaches us that not every well-formed question has an answer, and some definitions lead only to contradiction. Key takeaways. 1. Self-reference can create unsolvable paradoxes. 2. Not all collections can be treated as valid sets. 3. Careful formal systems must prevent such contradictions. 4. The paradox changed mathematics forever. 5. Its lessons remain relevant across multiple fields. The paradox of omnipotence. Can God create a stone so heavy he can't lift it? Introduction. The paradox of omnipotence is one of the most enduring theological and philosophical puzzles concerning the nature of divine power. At its core, it questions whether an all-powerful being can create limitations on its own power, creating a logical contradiction that challenges traditional understandings of omnipotence. The classic formulation. The paradox is typically presented as a two-part question. 1. Can an omnipotent being create a stone so heavy that it cannot lift it? 2. If yes, then there is something it cannot do, lift the stone. 3. If no, then there is something it cannot do, create such a stone. This creates an apparent contradiction in the concept of unlimited power. Either the being cannot create the stone, not omnipotent, or cannot lift the stone, not omnipotent. Therefore, true omnipotence seems impossible. Historical context. The paradox has roots in medieval theology. First appeared in Islamic theological debates, 11th century. Later discussed by Christian philosophers like Thomas Aquinas. Modern formulation attributed to philosopher J. L. Mackie, 1950s. Philosophical significance. The paradox challenges several key concepts. 1. Definition of omnipotence. What does all-powerful truly mean? Does power include logically impossible acts? 2. Nature of God. How to reconcile perfect power with logical consistency. Implications for theistic belief systems. 3. Limits of language. Whether such questions are meaningful. Problems with self-referential statements. Theological responses. Various religious traditions have proposed solutions. 1. Semantic solutions. The question is a misuse of language. Cannot doesn't apply to an omnipotent being. The paradox stems from faulty definitions. 2. Logical solutions. Omnipotence doesn't include logically impossible acts. Creating an unliftable stone is a meaningless concept. True power means ability to do what's possible. 3. Redefining omnipotence. Power as ability to actualize any possible state of affairs. Not about performing contradictions. Focus on maximal capacity rather than absolute power. Philosophical approaches. Secular philosophers have analyzed the paradox differently. 1. Paradox as nonsense. The question is grammatically correct, but logically empty. Similar to asking, can God create a square circle? 2. Modal approaches. Distinguishing between possible and impossible powers. Omnipotence only extends to metaphysically possible acts. 3. Process philosophy. Suggesting power is relational rather than absolute. God's power evolves with creation. Modern interpretations. Contemporary discussions focus on 1. Analytic philosophy. Precise definitions of power terms. Distinguishing between Unlimited capacity, ability to perform contradictions. 2. Logical consistency, whether the paradox reveals limits in our logic systems. How to talk meaningfully about infinite power. 3. Computer science analogies, comparing to system permissions. The superuser problem in computing. Related paradoxes. Similar logical puzzles include 1. The omnipotence paradox suite. Can God create a being more powerful than himself? Can God cease to be omnipotent? 2. The problem of evil. If God is all-powerful and good, why does evil exist? 3. The paradox of the stone. Variant focusing on destruction rather than creation. Cultural impact. The paradox has influenced 1. Religious discourse. Ongoing debates in theology. Interfaith discussions about divine attributes. 2. Popular culture. Appears in literature and film. Common example in philosophy courses. 3. Skeptical movements. Used to challenge traditional theism. Appears in atheist-theist debates. Potential resolutions. Major proposed solutions include 1. The Aquinas approach. Omnipotence means power to do what is possible. Contradictions are non-things, not limitations. 2. The Mavros solution. Distinguishes between task-defining power, task-performing power. 3. The Cartesian view. God can do the logically impossible. Human logic doesn't limit divine power. 4. The linguistic solution. The paradox misuses the word cannot. Properly understood, no contradiction exists. Implications for theology. The paradox forces reconsideration of 1. Divine attributes. How to define God's qualities consistently. Relations between power, knowledge, and goodness. 2. Religious language. How humans can meaningfully discuss the divine. Limits of analogical language about God. 3. Theodicy. Connects to problems of evil and suffering. How power relates to other divine qualities. Philosophical consequences. Beyond theology, the paradox affects 1. Epistemology. How we understand concepts of infinity. Limits of human understanding. 2. Logic systems. Development of paraconsistent logics. Handling of contradictory statements. 3. Metaphysics. Nature of possibility and impossibility. Conceptual boundaries of power. Contemporary status. Current perspectives include 1. Majority view. The paradox is resolvable with proper definitions. Doesn't disprove omnipotence, just clarifies it. 2. Minority view. Reveals genuine problems with omnipotence. Suggests need to revise traditional theism. 3. Neutral view. Highlights limits of human conceptualization. Shows difficulty in discussing transcendent concepts. Conclusion. The paradox of omnipotence remains a valuable intellectual exercise that 1. Tests the limits of theological definitions. 2. Challenges our understanding of power. 3. Demonstrates the importance of precise language. 4. Continues to inspire philosophical inquiry. While various solutions have been proposed, the paradox serves primarily as a tool for sharpening our concepts of divinity, power, and logical consistency, rather than as a definitive disproof of omnipotence. Key takeaways. 1. The paradox questions absolute definitions of power. 2. Multiple philosophical and theological solutions exist. 3. The debate continues to evolve. 4. The core issue involves language and logic. 5. Remains relevant across disciplines. The unexpected hanging paradox, a comprehensive analysis. Introduction. The unexpected hanging paradox is a fascinating logical puzzle that challenges our understanding of prediction, knowledge, and self-reference. First formulated in the 1940s, this paradox has puzzled mathematicians, philosophers, and logicians for decades. It presents a scenario where a prisoner faces an execution that is both predictable and unpredictable, creating an apparent contradiction. The classic formulation. The paradox is typically presented as follows. A judge tells a prisoner, "You will be hanged at noon on one of the next 7 days, but you will not know which day until the executioner comes to your cell that morning." The prisoner reasons, 1. The hanging cannot be on the 7th day, because if it hadn't happened by the 6th day, he would know it must be on the 7th. 2. Therefore, the last possible day is the 6th. But then it can't be on the 6th day either, because by the 5th evening he would know. 3. Following this logic, he eliminates each day in turn, concluding the hanging cannot occur at all. 4. Yet, the judge hangs him on Wednesday, a day he didn't expect, making the judge's statement true. Key elements of the paradox. 1. The surprise condition. The prisoner must not know the day beforehand. 2. The finite time frame. Execution must occur within specified days. 3. The prisoner's logical deduction. 4. The apparent contradiction between prediction and surprise. Historical background. The paradox first appeared in academic literature in the 1940s, with variations appearing earlier. Key developments include 1943, first known formulation by Swedish mathematician Lennart Ekebom. 1948, appeared in the British magazine Mind. 1950s, gained prominence through philosopher Michael Scriven's work. 1960s, logicians like Willard Quan van Orman Quine analyzed idea. Philosophical significance. The paradox raises fundamental questions about 1. Nature of knowledge and prediction. 2. Limits of deductive reasoning. 3. Self-referential statements. 4. The relationship between truth and belief. Mathematical perspective. Logicians have approached the paradox through 1. Epistemic logic, logic of knowledge. 2. Temporal logic. 3. Game theory. 4. Probability theory. Key interpretations include: the prisoner's reasoning contains a hidden flaw. The judge's statement creates a logical contradiction. The scenario involves an impossible self-reference. Psychological aspects. The paradox plays with human cognition. 1. Our tendency toward recursive thinking. 2. How we process self-referential information. 3. The limits of anticipation and surprise. 4. Cognitive biases in prediction. Potential resolutions. Several solutions have been proposed. 1. The logical error solution. The prisoner incorrectly eliminates days. His reasoning contains a hidden assumption. The elimination process is flawed. 2. The levels of knowledge approach. Distinguishes between knowing the rules, knowing that others know the rules, knowing that others know that you know, etc. 3. The temporal consideration. The surprise must be evaluated at each moment. What seems impossible in advance becomes possible in real time. 4. The game theoretic solution. Views it as a game between judge and prisoner. The judge has a winning strategy. Variations of the paradox. Similar puzzles include 1. The surprise test paradox. Teacher announces unexpected test. 2. The unexpected egg, which box contains the surprise egg. 3. The bottle imparadox, self-referential promises. Applications in other fields. The paradox has relevance to 1. Computer science, algorithm design, artificial intelligence prediction, cryptographic protocols, 2. Economics, market prediction, game theory applications, decision theory. 3. Law, legal reasoning, contract interpretation, jury decision-making, cultural impact. The paradox has appeared in 1. Literature, science fiction stories, mystery novels, philosophical works. 2. Popular culture, television shows, puzzle books, online forums. 3. Education, logic courses, mathematics curricula, philosophy classes, modern interpretations. Current thinking includes 1. Bayesian approaches, updating probabilities day by day, modeling changing expectations. 2. Cognitive science perspectives, how humans process paradoxical information, neural basis of surprise. 3. Computational modeling, simulating the scenario, testing different reasoning strategies. Why the paradox matters. This thought experiment is valuable because 1. Reveals limits of formal reasoning. 2. Demonstrates complexity of prediction. 3. Highlights problems with self-reference. 4. Provides insights into knowledge and belief. Conclusion. The unexpected hanging paradox remains an important intellectual challenge that 1. Tests our logical framework. 2. Challenges intuitive reasoning. 3. Demonstrates complex interactions between knowledge and time. 4. Continues to inspire new analyses. While various solutions have been proposed, the paradox continues to stimulate discussion about the nature of surprise, prediction, and the limits of deductive reasoning. Key takeaways. 1. The paradox combines prediction with surprise. 2. It reveals problems with self-referential reasoning. 3. Multiple disciplines have attempted solutions. 4. It remains relevant to understanding knowledge and expectation. 5. The core issues continue to inspire research. Schrödinger's cat, exploring quantum superposition through a famous paradox. Introduction. Schrödinger's cat is one of the most famous thought experiments in quantum physics, conceived by Austrian physicist Erwin Schrödinger in 1935. This paradoxical scenario was designed to illustrate the apparent absurdity of quantum superposition when applied to macroscopic objects. At its heart, the paradox challenges our understanding of reality by proposing that a cat in a sealed box could be simultaneously alive and dead until observed. The original thought experiment. Schrödinger's original formulation proposed 1. A cat is placed in a sealed steel chamber. 2. Alongside a device containing a tiny amount of radioactive substance, a Geiger counter, a hammer, a flask of poison gas. 3. If a single atom decays, the Geiger counter triggers. Hammer breaks the flask. Poison gas is released. Cat dies. 4. If no decay occurs, the cat lives. 5. After 1 hour, quantum mechanics suggests the atom exists in superposition, decayed, not decayed. Therefore, the cat exists in superposition, alive, dead, until the box is opened and observed. Quantum mechanics background. The paradox stems from key quantum principles. 1. Wave function superposition. Quantum systems can exist in multiple states simultaneously, described by a wave function encompassing all possibilities. Only collapses to one state upon measurement. 2. Copenhagen interpretation. Dominant early quantum theory states quantum systems exist as probabilities until observed. Observation forces collapse to definite state. 3. Quantum entanglement. The cat's fate becomes entangled with the atom's state. Creates macroscopic superposition. Purpose of the paradox. Schrödinger intended to 1. Highlight apparent absurdities in quantum theory. 2. Challenge the Copenhagen interpretation. 3. Demonstrate macroscopic consequences of quantum rules. 4. Question the role of observation in reality. Modern interpretations. Various approaches attempt to resolve the paradox. 1. Many worlds interpretation, 1957. All possibilities become real. Universe splits into branches. One with live cat, one with dead cat. No true collapse occurs. 2. Quantum decoherence. Environmental interactions destroy superposition. Explains why we don't see macroscopic superpositions. Occurs before observation. 3. Objective collapse theories. Wave function collapses spontaneously, not dependent on observation. Explains definite outcomes. 4. Quantum Bayesianism. Quantum states represent knowledge, not reality. Superposition reflects observers' uncertainty, not an objective property. Experimental progress. While we can't put cats in superposition, modern experiments explore similar concepts. 1. Quantum optics. Photons in superposition states. Delayed choice experiments. Quantum eraser experiments. 2. Matter-wave interference. Large molecules, e.g. buckyballs, show wave nature. Demonstrates quantum behavior in larger systems. 3. Quantum computing. Qubits maintain superposition. Error correction handles decoherence. Scaling challenges remain. Philosophical implications. The paradox raises profound questions. 1. Nature of reality. Does observation create reality? What constitutes a measurement? Where is the quantum classical boundary? 2. Consciousness role. Whoa. Does consciousness cause collapse? Can machines perform measurements? Hard problem of quantum observation. 3. Macroscopic quantum effects. How large can superposition get? Why don't we see quantum weirdness daily? Emergence of classicality. Practical applications. Understanding the paradox has led to 1. Quantum technologies. Quantum cryptography. Quantum sensors. Quantum imaging. 2. Foundational research. Tests of quantum foundations. Interpretational debates. New experimental techniques. 3. Information theory. Quantum information science. Entanglement applications. Quantum communication. Common misconceptions. Several misunderstandings persist. 1. The cat is both alive and dead. More accurately described as indefinite state. Not a mixture but a true superposition. 2. Consciousness causes collapse. Not part of standard quantum theory. Measurement can occur without observers. 3. This proves quantum theory is wrong. Actually demonstrates its strange consequences. Not a disproof but a challenge to interpretation. Current research frontiers. Scientists continue exploring related concepts. 1. Macroscopic superposition. Creating larger quantum systems. Quantum optomechanics. Superconducting qubits. 2. Quantum classical boundary. Identifying transition points. Decoherence mechanisms. Emergence of classicality. 3. Alternative interpretations. Relational quantum mechanics. Transactional interpretation. Quantum Darwinism. Cultural impact. The paradox has influenced 1. Popular culture. Numerous sci-fi references. Appears in films, TV shows. Common in science communication. 2. Language. Schrödinger's EX meme format. Used metaphorically in various fields. Symbol of quantum weirdness. 3. Philosophy. Discussions of realism. Nature of existence. Observer effects. Future directions. Key areas for future exploration. 1. Larger quantum systems. Pushing superposition size limits. Quantum biology investigations. New materials for quantum effects. 2. Interpretation tests. Mental discrimination. New theoretical framework. Foundational experiments. 3. Quantum gravity. What? Combining with relativity. Space-time superpositions. Quantum measurement in cosmology. Conclusion. Schrödinger's cat remains profoundly significant because it 1. Challenges classical intuitions. 2. Bridges quantum and classical worlds. 3. Stimulates ongoing research. 4. Inspires philosophical inquiry. 5. Demonstrates quantum theory's strangeness. While originally intended as criticism, the paradox has become a valuable teaching tool, a driver of quantum foundations research, a cultural touchstone for quantum physics, a reminder of reality's counterintuitive nature. The thought experiment continues to push our understanding of quantum mechanics and its implications for the nature of reality itself. Zeno's paradox, Achilles and the Tortoise, a complete analysis. Introduction. Zeno's paradox of Achilles and the Tortoise stands as one of the most enduring thought experiments in philosophy and mathematics. Formulated by the ancient Greek philosopher Zeno of Elea in the 5th century BCE, this paradox challenges our fundamental understanding of motion, infinity, and the nature of reality itself. At its core, it appears to demonstrate that swift Achilles can never overtake a slower tortoise, given a head start, despite our everyday experience suggesting otherwise. The original paradox. Zeno's formulation presents this scenario. 1. Achilles races against a tortoise. 2. The tortoise gets a head start of 100 meters. 3. When Achilles reaches the tortoise's starting point, the tortoise has moved forward, say, 10 meters. 4. When Achilles covers that 10 meters, the tortoise moves another 1 meter. 5. This process continues indefinitely. 6. Conclusion. Achilles never catches the tortoise. Mathematical representation. The paradox can be expressed as an infinite series. 100 m 10 10 10 on 0.0 m 0.0 on m out 111.1 on. Nensudais, not with you well. Meters. This infinite sum converges to a finite distance, 111.19 meters, where Achilles would overtake the tortoise if the race continued indefinitely. Historical context. 1. Developed by Zeno, 430 BCE. 2. Part of a series of paradoxes about motion. 3. Intended to support Parmenides' philosophy that change and motion are illusions. Reality is fundamentally unchanging. 4. Preserved through Aristotle's physics. Philosophical implications. The paradox raises profound questions about 1. The nature of infinity. 2. The continuity of space and time. 3. The relationship between mathematics and physical reality. 4. The validity of sensory experience. Mathematical resolutions. Several approaches have resolved the paradox mathematically. 1. Infinite series convergence. The distances form a geometric series. Sum A, 1R, 100, 10.1, 111.19 meters. Achilles passes the tortoise at this point. 2. Calculus solution. Reformulated using limits and derivatives. Velocity difference ensures overtaking. dt dx wave, finite time, solution. 3. Discrete mathematics. Modern treatments using quantum concepts. Planck length as minimum distance. Eliminates true infinite divisibility. Physical resolutions. Physics provides additional perspectives. 1. Atomic theory. Matter composed of discrete particles. Space not infinitely divisible. Minimum meaningful distances exist. 2. relativity considerations, finite speed of information, quantum foam at smallest scales, time quantization theories. 3. Kinematic solutions. Relative velocities determine overtaking, finite time for any finite distance, acceleration factors in real motion, modern interpretations. Contemporary views include 1. Process philosophy. Reality is sequences of events. Motion as fundamentally quantized. Rejects perfect continuity. 2. Mathematical constructivism. Rejects actual infinities. Only potential infinities exist. Limits mathematical treatment. 3. Physical limits. Planck scale restrictions. Quantum measurement limits. Information theory constraints. Related paradoxes. Zeno created several similar paradoxes. 1. The dichotomy paradox. Can't reach destination. Must first cover half the distance, then half the remaining, etc. 2. The arrow paradox. At any instant, arrow occupies space, thus not moving at that instant, therefore never truly moves. 3. The stadium paradox. Relative motion contradictions. Challenges assumptions about space-time. Educational applications. The paradox remains valuable for teaching. 1. Mathematical concepts. Infinite series. Limits and convergence. Asymptotic behavior. 2. Physical principles. Kinematics. Relative motion. Quantum effects. 3. Philosophical thinking. Nature of reality. Limits of human perception. Relationship of math to world. Cultural impact. The paradox has influenced 1. Literature. Referenced in works from Borges to modern sci-fi. Appears in philosophical fiction. 2. Popular science. Common example in physics books. Frequently used in educational media. 3. Artistic representations. Visual art exploring infinity. Musical compositions. Performance art pieces. Current scientific consensus. While mathematically resolved, the paradox still informs 1. Mathematical physics. Treatments of infinities. Renormalization techniques. Quantum field theories. 2. Philosophy of science. Nature of mathematical truth. Relationship of models to reality. Limits of scientific explanation. 3. Cognitive science. How humans perceive motion. Neural processing of continuity. Psychological aspects of paradoxes. Future directions. Ongoing research areas include 1. Quantum gravity. Nature of spacetime at smallest scales. Potential discrete structure. Emergent spacetime theories. 2. Information physics. Physical limits of computation. Universe as information processor. Digital physics approaches. 3. Consciousness studies. Perception of continuity. Neural basis of motion perception. Cognitive models of infinity. Conclusion. Zeno's Achilles and the Tortoise paradox remains profoundly relevant after 2,500 years because it 1. Challenges fundamental assumptions. 2. Bridges philosophy and mathematics. 3. Illustrates deep concepts simply. 4. Continues to inspire new thinking. 5. Demonstrates the power of thought experiments. While mathematically resolved through calculus and infinite series, the paradox still serves as a valuable teaching tool, a stimulus for philosophical inquiry, a reminder of the complexity underlying simple observations, a testament to ancient Greek intellectual achievement. The paradox ultimately reveals more about how we understand reality than about reality itself, making it eternally fascinating for thinkers across disciplines. The twin paradox, a comprehensive guide to Einstein's time dilation thought experiment. Introduction. The twin paradox stands as one of the most fascinating demonstrations of Einstein's theory of special relativity. This thought experiment reveals how time behaves differently for observers moving at different velocities, particularly at speeds approaching the speed of light. First conceptualized in the early 20th century, it continues to challenge our intuitive understanding of time and space. Understanding the basic scenario? The classic formulation presents this situation. 1. Identical twins are born on Earth. 2. One twin remains on Earth. Twin A. 3. The other twin embarks on a space journey at near light speed. Twin B. 4. After traveling to a distant star and returning. 5. The spacefaring twin returns younger than the Earthbound sibling. This apparent paradox emerges because, from Earth's perspective, the traveling twin's clock runs slower due to high velocity. From the spaceship's perspective, Earth appears to be moving rapidly away. Yet only the traveling twin experiences actual time dilation. The physics behind the paradox. Special relativity explains this phenomenon through two key principles. 1. Time dilation. Time intervals measured in a moving frame appear longer to a stationary observer. Mathematically expressed as I2pt where 1 v d ca. At 90% light speed, 0.9 c time slows to about 44% of Earth time. 2. Relativity of simultaneity. Events simultaneous in one frame aren't necessarily simultaneous in another. This breaks the symmetry between the twins' perspectives, resolving the paradox. The apparent contradiction resolves when considering 1. Asymmetric acceleration. The traveling twin experiences acceleration when leaving Earth, turning around at the distant star, decelerating upon return. These accelerations mark objective changes in reference frames. 2. Proper time calculation. WA. The traveling twin's path through spacetime is objectively shorter. This results in less experience time, proper time. The Earth twin's path is longer in spacetime terms. 3. Minkowski spacetime diagrams. Visual representations show world lines for both twins, different spacetime intervals, clear demonstration of non-symmetric aging. Mathematical demonstration. Consider a 20 light-year journey at 0.8 c. For Earth twin. Total time, GA. Distance velocity, QA, 20.8, 50 years. For traveling twin, including time dilation, years. Perceived time, UA, 51.6, 720 years. Returns 20 years younger than Earth twin. Experimental verifications. While we can't send humans at relativistic speeds, multiple experiments confirm time dilation. 1. Atomic clocks on aircraft. Hafele Keating, 1971. Flew atomic clocks around the world. Measured nanosecond level time differences. Matched relativistic predictions. 2. Particle accelerators. Muons, subatomic particles, normally decay in microseconds. At near light speeds, their observed lifetime extends significantly. 3. GPS satellite systems. Must account for special relativistic time dilation, 7 AS day. General relativistic effects, 45 AS day. Total compensation, I-30 AS day. Common misconceptions. Several misunderstandings persist about the paradox. 1. It's symmetrical. 1. False. Only the traveling twin changes inertial frame. The Earth twin remains in a single inertial frame. 2. Acceleration alone causes it. Not exactly. The different spacetime paths are key. Acceleration simply marks the frame changes. 3. It violates relativity. Actually confirms relativity's predictions. The asymmetry comes from non-inertial motion. Philosophical implications. The paradox raises profound questions about 1. Nature of time, nature, challenges the Newtonian absolute time concept, establishes time as relative to observer's state of motion. 2. Human perception. Our intuition fails at relativistic scales, requires abstract mathematical thinking. 3. Reality of time dilation, not just an apparent effect, represents actual physical difference in experienced time. Applications in modern physics. Understanding the paradox helps with 1. Space travel planning, accounting for time effects in interstellar missions, considering biological impacts on astronauts. 2. Particle physics, explaining extended particle lifetime, designing high-energy experiments. 3. Cosmology, modeling distant, fast-moving celestial objects, understanding relativistic jets from black holes. Future possibilities. While currently limited to thought experiments and microscopic observations. 1. Potential future tests. Ultra-high-speed spacecraft, improved atomic clock, quantum systems exhibiting relativistic effects. 2. Theoretical extensions, incorporating general relativity, examining quantum mechanical versions, exploring cosmological implications. Conclusion. The twin paradox remains one of the most illuminating demonstrations of special relativity's consequences. While initially seeming paradoxical, careful analysis reveals it as a powerful confirmation of Einstein's revolutionary theory. Key takeaways include 1. Time is relative to the observer's motion. 2. Acceleration breaks the symmetry between observers. 3. The effect has been experimentally verified. 4. It fundamentally changes our understanding of time. 5. Practical applications exist in modern technology. This thought experiment continues to inspire physicists and philosophers alike, serving as a gateway to deeper understanding of our relativistic universe. The Ship of Theseus, a deep dive into the identity paradox. Introduction. The Ship of Theseus is one of the most enduring thought experiments in philosophy, dating back to ancient Greek thinkers. This paradox questions the fundamental nature of identity and continuity by examining what happens when all components of an object are gradually replaced. At its core, it challenges our understanding of what makes something fundamentally itself over time. The original paradox. The classic formulation presents this scenario. 1. Theseus's ship is preserved in a harbor as a historical artifact. 2. Over time, its wooden planks decay and require replacement. 3. Each old plank is removed and a new one is installed. 4. This process continues until every original component has been replaced. 5. The central question. Is this still the same Ship of Theseus? Variations and extensions. Philosophers have explored several versions. 1. The complete replacement version. All original materials are eventually substituted. No physical connection to the initial object remains. 2. The reconstructed version. The original removed planks are collected. Someone reassembles them into a ship. Which ship is the real Ship of Theseus? 3. Gradual versus instant replacement. Does the speed of replacement affect identity? What if changed all at once versus slowly over years? Historical context. The paradox has roots in 1. Ancient Greek philosophy, Plutarch's writings. 2. Heraclitus's river fragments about change. 3. Buddhist concepts of impermanence. 4. Early modern philosophy, Hobbes, Locke. Philosophical perspectives. Major schools of thought offer different interpretations. 1. Essentialism. 1. Objects have core, unchanging essences. Identity persists if essence remains. Challenges. Defining what constitutes essence. 2. Continuity theory. Gradual change preserves identity. Small steps maintain connection. Problems. When does it stop being original? 3. Mirological nihilism. Objects don't truly persist over time. Only temporal parts exist. Radical solution denying persistence. 4. Four-dimensionalism. Objects extend through time, composed of temporal parts. The whole includes all time slices. Modern applications. The paradox informs contemporary discussions. 1. Personal identity. Are we the same person over time? Cellular replacement in human bodies. Psychological continuity. 2. Digital preservation. Software updates and versioning. Digital artifact conservation. Blockchain immutability concepts. 3. Art restoration. Conservation ethics. How much can be changed before it's different? Authenticity debate. Scientific perspectives. Modern science adds new dimensions. 1. Biological replacement. Human cells regenerate completely every 7-10 years. Are we biologically the same people? 2. Quantum physics. Particle replacement at atomic levels. No permanent material substrate. 3. Information theory. Pattern persistence versus material persistence. Information as the conserved element. Thought experiment variations. Similar paradoxes explore related concepts. 1. Triggers broom, only handle and head replaced. 2. The Achilles of Theseus, double replacement. 3. The human body, complete cell replacement. 4. The digital ship, software version changes. Cognitive science insights. How humans perceive object identity. 1. Psychological essentialism. Innate tendency to attribute essences. Developmental aspects of identity concept. 2. Gestalt principles. Whole perceived differently than part see. Pattern recognition in identity. 3. Memory's role. How recollection shapes identity perception. Narrative construction of continuity. Mathematical modeling. Formal approaches to the paradox. 1. Category theory. Objects as networks of relationships. Identity through morphisms. 2. Topology. Yes. Continuous transformations. Homeomorphic equivalence. 3. Mirror topology. Combines parts and connections. Formalizes continuity conditions. Practical implications. Real-world consequences. 1. Legal contexts. Property identity over time. Inheritance and artifact ownership. 2. Museum conservation. Restoration standards. Authenticity certifications. 3. Product life cycles. Versioning in manufacturing. Replacement part policies. Cultural references. The paradox appears in 1. Literature. From ancient texts to modern sci-fi. Jorge Luis Borges's writings. 2. Popular culture. TV shows, Doctor Who, Westworld. Film references. Video game narratives. 3. Language. Thesin as adjective. Common analogy in discussions. Philosophical developments. Recent scholarly work. 1. Process philosophy. Reality as continual becoming. Rejects static identity. 2. Object-oriented ontology. Objects independent of their qualities. Withdrawal from total knowledge. 3. Posthumanism. Identity in hybrid entities. Human-technology integration. Neuroscience perspectives. Brain mechanisms for identity. 1. Neural pattern consistency. How brains recognize persistent objects. Neural representations of identity. 2. Memory systems. Role in maintaining identity perception. Constructive nature of recall. 3. Self-models. Neurological basis of self-identity. body schema maintenance, future directions, emerging areas of inquiry. 1. Artificial identity, AI systems and persistence, machine learning model versioning. 2. Quantum identity, quantum object persistence, entanglement and identity. 3. Extended mind theory, identity beyond biological bounds, cognitive integration with tools. Conclusion: the Ship of Theseus remains vital because it 1. Challenges fundamental assumptions. 2. Bridges ancient and modern thought. 3. Applies across disciplines. 4. Resists definitive solution. 5. Continues to inspire new thinking. Key insights include: well, identity may be more about pattern than material. Continuity plays crucial psychological role. Context determines what we consider same. The paradox reveals our cognitive frameworks. Ultimately, the Ship of Theseus serves as a powerful philosophical tool, a lens for examining identity concepts, a bridge between abstract and practical, a testament to enduring philosophical questions.